Good morning once again, everybody. Well, so ladies and gentlemen, the next topic we're going to discuss on smart metering and cloud, key structure considerations. And we have Mr. Sainath right here as the next speaker for the session. Mr. Sainath from AWS comes with 2 decades of experience of working with customers in utilities and smart cities, domain in various roles, including architecture, strategy, consulting, process. And gentlemen, his recent assignments were around smart metering, billing, and customer care, smart city, advanced analytics, etc. He has worked earlier with IBM in their global COC environment and utility in India and abroad. Prior to working with IBM, he worked with Tata Power Delhi Distribution Limited in their IT team. Thank you all are ready. They're all sessions. I request Mr. Sainath to please take it forward.
Thanks, ma'am, for the introduction. So I'll get started. So what I'll be talking today is primarily about the key architectural considerations that should be considered by, say, utilities or the ISVs who are developing applications for, smart metering when deploying them on cloud. So what I'll be covering is one, in general, why are customers choosing cloud, and then I'll talk about specific to smart metering, where different kinds of functionalities that are being implemented or looked at in smart metering, and what are the different architectural challenges that could come up or that utilities have faced in the past, be it on-premise kind of implementation, and what are the different architectural considerations that utilities and the application developers or application providers should consider for the applications that they are implementing on cloud, right? And also for utilities who are considering cloud as the infrastructure layer where they want to implement their smart metering solutions, and example of, say, how one integration architecture would look like, or how the data would be flowing in the case of smart metering. So these are some of the aspects that I will be covering in today's presentation. So to start with, why do customers choose cloud in general, right? I mean, there are a few reasons or few benefits that customers see because of which they are moving towards cloud computing. One of the reasons is that you can stop spending money on running and maintaining data centers. Normally, when setting up applications or a new set of enterprise systems, usually set up data centers, which involves say leasing land, building big buildings, buying large servers, storage, setting up network, softwares to monitor those. So there is a lot of expenditure which happens in setting up these data centers, and at the same time maintaining these data centers, be it in terms of maintaining their physical security or facility management or HVAC, different areas, right? But in the case of cloud, all this heavy lifting is done by cloud solution providers like AWS, where we have data centers with the resources available, which the utilities customers can opt for based on the resources that they would need, which would mean which could be virtual machines, or it could be a database as a service, or it could be IoT platform as a service. So different resources which are available, which can be opted, and you pay based on what you use, right? So you're not spending money on running and maintaining data centers. Another reason is you can stop guessing capacity, right? So the example is that if, say, you are implementing smart metering system now, and you are planning to implement this on a on-premise data center, you have to guess the capacity which is needed for, say, 3 years or 5 years down the line. So you're starting with, say, 10,000 smart meters in the initial month, and over time you plan to increase to, say, 1 million smart meters. So today itself you'll have to try and guess how much storage would be needed, what computing resources would be needed 5 years down the line or 2 years down the line to accommodate 1 million meters, right? In the case of cloud, you don't have to guess that capacity, because you are taking capacity or using capacity based on the computing requirements that you have today, tomorrow, or this week, right? right? And you can opt for additional resources as you move along, as the meter volume increases, as the number of transactions increases, right? So because the resources would be available on demand, right? So you don't have to worry about capacity that you would be needing 3 years, 1 year, or 5 years down the line, right? Third one is you're trading capital expense for variable expense, like the example of setting up data centers, or setting up large servers, or storage or network. Uh, in that case, you are making a good amount of capital expenditure in setting up all this data center and the required infrastructure. But in the case of cloud, like I said, all this heavy lifting has already done by the cloud solution provider, and so you are not spending there, and rather you are doing a variable expense where you are paying for what you use, right? So if you are using one virtual machine, or an IoT platform which has to receive data from 1000 devices, you're paying only for that. You're paying for what you are using. You're not paying for something which you will probably use 2 years, 3 years down the line, right? And you are paying for what you use based on, say, a monthly basis, right? So you are trading your capital expense for variable expense, which actually eases the payment model, right? So another area is benefit from massive economies of scale. In order to cater to the requirements of customers, cloud solution providers like AWS, we get the infrastructure in large scale because of the large volume of customers that we cater to. And this massive economies of scale benefits us in terms of cost, and the customers are also benefited based on these economies of scale. Similarly, increase in speed and agility. So when, say, you're setting up a few basic systems today, like you're setting up, say, a billing system and a my application on cloud, right? And if, for example, you're setting it on premise in a data center, and 1 year later, once you gather good amount of data, you decide to go ahead and do analytics on top of it. If it is on a typical on-premise environment, it would take a few months for you to set up the infrastructure required to run AI, ML, or advanced analytics. And compared to cloud, where you can leverage new services on demand, like you want to set up a data lake, it's a service that you can opt for, right? And you provide access mechanisms and start using a data lake, right? And on top of that, you start building analytical models, which could be analytics models, or calculating KPIs, or building machine learning models. So your ramp up time is reducing from a few months to probably a few days or weeks. So that's how you are increasing the speed and agility. And another advantage is the pace at which you can replicate the environment into, say, another place. Like, for example, some of the application providers or application providers set up an environment for one utility, right? And they make improvements in their product, and they want to replicate this to another customer within the country, right? Or outside the country. So replicating this environment becomes much easier, because of things like, something what we call infrastructure as code. So infrastructure can be kept as code, and you replicate this code in another region or for another customer, right? So the time needed to go replicate the environment for another customer is reducing drastically, right? So these are some of the reasons why customers choose cloud, right? Now, moving specific to smart metering related aspects, there are different functional requirements in smart metering, right? And it is not just billing, though billing happens to be one of the most talked about topic, or the first milestone of a smart metering implementation. There are various other functional requirements in a smart metering project, right? So first, like I mentioned, billing using the AMI reads for multiple tariff types. It could be normal slab-based billing. It could be time of use based billing. So different types of billing which is done using the AMI reads, which we are getting from the smart meters. And similarly, automating connection changes, like it could be an automation of a move-in process where we do an on-demand read, do a remote reconnection. It could be a move out scenario, or it could be a category change, it could be load change. So different connection related changes which are being automated using AMI reads, or in that case, AMI commands as well. Right? And other functionalities could be that detecting potential fraud. One way of detecting potential fraud is based on the alarms which are sent by the smart meters. Right? Apart from this, a lot of indirect analysis can also be done to identify potential fraud. Like it could be a correlation between the alarms and the read data which is coming in, or the consumption which is happening in the consumer premise. Right? Another requirement could be that identification of outage or power quality issues, like the outage and restore alarms that come in, or the power quality issues that come in, and more importantly, filtering this data in near real time, right? Getting the outage or power quality, say under voltage or SAGSWell data directly and using it may not be a straight answer, right? It would also need good amount of analysis of this data, filtering of data to identify whether it's a feeder level outage, transformer level outage, or a single light out customer. So different kinds of filtering is applied on this data, especially in cases where some of the outages, sometimes the outage alarms come in large volumes, right? When the outage happens, say, at the feeder level. So the filtering which is needed needs a lot of processing, and analysis is done before an action is decided. So other requirements could be in terms of device operation and maintenance, which could be, say, firmware updates or configuration updates, which are done on smart meters or the data concentrators which are implemented, right? Or the communication modules which are there inside the smart meters. Okay? And another requirement that is being looked at is in terms of advanced analytics use cases, which could be near real time or non real time, based on the data which is coming in, like it could be alarms or events, or it could be running AI/ML for customer segmentation, or it could be for fraud detection. So a lot of advanced analytics use cases are also being planned on top of the smart meter data which is coming in. And the last but not the least, enabling new services, like based on the smart meter functions. Prepayment is one of the functionalities which is planned to be taken up at a large scale, right? So prepayment primarily with the balance calculation, or reconnect, disconnect, all this happening from the enterprise layer rather than the meter layer, right? A few more areas could be, say, time of use or demand response. So these are some of the functional requirements beyond billing which are being looked at in smart metering, and these functionalities have significant impact on not just two applications or few smart meters that we have to implement, but the impact is much larger, right? So when I say much larger, it could be tens of business processes undergoing change. The business processes would be related to, say, billing, it could be customer care, it could be meter reading, it could be the process in which the meters are removed or the meters are repaired. So there could be tens of business processes which will undergo change. And when we say tens of business processes, obviously there will be multiple business units which will be involved. Again, say the metering team, billing team, warehousing team, customer care team. So many business units who will be involved in this value chain. And in order to achieve this, there are multiple applications which are implemented and enhanced. It is not just HES and MDMS that we are implementing, but tens of applications which are enhanced. It could be billing and customer care. It could be, say, outage management system. It could be workforce management, and some utilities could be having a different workforce management for, say, meter installation, a different workforce management to attend to meter faults, or similarly a different application for fuse of call compliance, or a different application for commercial compliance. So there could be multiple applications based on customer to customer or utility to utility, where the application enhancements need to be done, right? And this would mean multiple application integration interfaces, which could be through different methods. We can't make a broad statement that all integration for AMI would happen based on web services, right? So there could be legacy applications which might be integrated using say CSV files, for example. right? So there could be multiple integration methods, and we should be prepared to cater to these kind of requirements when we are implementing smart metering. And similarly, variable workloads, some applications would be needing different workloads, higher performance requirement during certain times of the day, right? Like for example, you want to run a bulk work order creation in your workforce management, right? So tomorrow 10,000 meters have to be installed, so you have to create 10,000 work orders tonight, right? And rest of the day the workload on workforce management could be lesser. So different types of workloads which would be needed. Similarly, thousands to millions of near real-time alarms, which totally depends on field conditions. We can't really predict, what would be the volume or what could be the volume of alarms which could be coming in real time and hitting the head-end system and then probably MDM system, right? And then, the subsequent systems which would be needing it. So, and terabytes of data collected. It could be structured, unstructured, different types of data which is collected. So that means, these functional requirements, if these are to be addressed, there are different architectural challenges which could come up, and utilities and the application providers have to prepare themselves to address these architectural challenges which come in smart metering projects, right? So one, like we discussed, scalability, there could be scenarios where the implementation of 1,000 meters or 5,000 meters, everything is smooth, but you are actually scaling up this volume to say 1 million, then there could be scalability issues, like running the VE process is taking more time than you actually planned, right? Or one on-demand read transaction is taking more time than you actually planned, right? And there could be meter alarms and DCUs flooding, like the example that I took before. So there could be 1 or 5 feeders which suddenly went down, and smart, pardon. So the smart meters are flooding alarms on to the head-end system, right? Similarly, there could be integration requirements. Primarily, the integration requirements could be through multiple integration methods. Like billing could be asking for some interfaces could be based on flat files, some interfaces could be queue-based integration, some could be say REST API-based integration. So we can't go with the standard approach that all integration will be based on flat files or based on web services. We should have that flexibility of addressing multiple integration methods. Right. Thirdly, the data, a huge amount of data is collected, and sometimes what happens is, we assume that over a 6 months time period, the storage which would be needed to maintain this data is say 20 TB or 100. I'm just giving an example, right? It could be 50 TB, and this data could be, structured data or unstructured data. About 6 months down the line, you may realize that, you bought storage in your data center only for 50 TB, but it is full within 3 months, right? So that's when you end up purging the data or deleting the data, which could be very useful for you in the long run. So these are some of the architectural challenges that are faced. And similarly, the applications could be monolith in nature, or they may not support stateful or stateless kind of a situation, right? And the effort which is needed for implementing on-premise applications, there would be good amount of effort in deploying them, right? Like setting up applications, configuring them, installing them, ensuring they are working fine. Or it could be administrative efforts in terms of monitoring the health of servers or health of network, or configuring the network. So all these are some of the architectural challenges that we face on-premise implementation or a typical data center kind of a implementation, right? And next few slides, what I'll be talking about is some of the key architecture considerations, some of keeping in view the points that I explained in the previous slides. Right, key architecture considerations that utilities can consider when they are planning their smart metering implementation on cloud, or the application providers who are planning to roll out their applications or smart metering applications on cloud. Right? So what I'll cover is basically these considerations, grouped into 5 categories. And these 5 categories are based on something what we call as AWS well-architected framework. So this AWS well-architected framework is a set of guiding principles which were prepared based on AWS experience of working with many customers and application providers in implementing applications on cloud. So I'll explain these in the context of taking examples of smart metering implementation and cover those architecture considerations. Right. First one will be around performance efficiency. Performance efficiency is an important factor, not just for smart metering, but the applications that we implement in general. Right. In the case of smart metering, it could be the example that I mentioned before. That in the initial case when there were just 1,000 smart meters, one on-demand read was probably taking say 1 minute. But when you increase to 1 million, the number of transactions increased, and it is probably taking more time. Right. The impact of this would be that a customer who is waiting to take his bill has to wait for more time than what he actually used to earlier. Right. So in order to look at the performance efficiency, some of the aspects that they can consider is using serverless architectures on cloud. So when we say serverless architectures, you are not, the underlying infrastructure and the resources needed are provided by the cloud solution provider, and you are deploying your application on a serverless architecture. Right? So that means you are not setting up virtual machines, you are not defining what are the scaling requirements, you are not sizing in advance. So all these are maintained by the cloud solution provider. In the case of AWS, it could be AWS Lambda, or it could be say API gateway, wherein you're not defining the servers, but based on the load which is coming on to your application, the underlying resources scale up or scale down to meet the requirement. Okay? Another one could be in terms of democratizing advanced technologies and opt for dependent services. So there are different services which will be available on cloud. Like it could be say advanced analytics, which could be based on machine learning, and all your IT team may not be equipped on machine learning. Right. So in that case, you could look at managed services, where some of the responsibility of managing those services goes on to the cloud solution provider, and your IT team can focus on developing the actual say algorithms. Right. And another one would be using purpose-built databases. When we talk about cloud, there would be multiple database options which would be available. In the case of AWS, it could be say RDBMS-based databases. It could be NoSQL databases. It could be graph database. So there are multiple options available. And when you're implementing a smart metering application, you should look at using purpose-built databases and not just one database to run the entire say HES or MDMS. If you think that for a certain set of transactions a NoSQL database is good, then you should use NoSQL database for such type of transactions. Right. So it is always good to use purpose-built databases so that the required performance is delivered when you are actually running the application. Right. Another area could be, in terms of operational excellence. So once you have implemented your applications and you're running those applications, it is important to, monitor the operations based on which you can improve the operations level. Like for example, what is the execution time which is taking to run some of the key AMI processes, right? How much time is one remote reconnection is taking, or one firmware update is taking, or one reconnection is taking. So it is good to measure these execution times so that you know that this is the area where improvement would be needed, right? So when you talk about say on-demand read, there would be a billing application, MDM, HES, talking to the meter, and again this entire chain. So if you measure these execution times, that is where you know that this is the area where I need to improve the overall process or the execution time. So you can use various cloud native resource monitoring tools to achieve some of these measurement processes. And at the same time, you should also be performing pre-mortems to anticipate failures. Right? So in the same example of on-demand read, say there are 5 applications in this whole value chain of running an on-demand read. And what if one of the application fails in between? Right? What procedure do you have if one of the applications in this value chain fails and you could not get the on-demand read from the meter? Right? So you should anticipate failures and you should create procedures to handle that. right? So another area would be reliability. So reliability means the ability of a workload to perform its intended function correctly and consistently. So for this, you can look at using things like auto scaling when deploying on cloud. So auto scaling means the auto scaling policies will be defined based on which the resources will be scaling up or down based on the load requirements, right? Like for example, there would be good amount of load on HES early in the morning when the entire bulk of data or read data is gathered from the meters, and rest of the day the load may not be as high as that. So that is when you would need auto scaling on HES so that it can cater to that extra load on the servers, and rest of the day you may not need the load, right? So the advantage of this is you're catering to the load which is needed. At the same time, commercially you are at advantage because you are paying only for those few hours of additional resources that you're taking and not for the entire day. Right? And you can define mechanisms to automatically recover from failure. Like for example, in this case where the previous example where I talked about on-demand read, if one of the applications in this value chain fails, say for example, one of the servers of HES fails, right? So we can define mechanism to automatically recover and spin up another HES so that it can cater to the overall load which is falling onto HES. So we should try and define the mechanisms to automatically recover from failure. And another way is to scale horizontally to increase aggregated load availability, right? And security is an important aspect. Security in terms of protecting data in transit and at rest, and this needs to be applied at multiple layers. When I say multiple layers, at the network layer, at the what ports to be opened, which ports to be open to which set of IP addresses, or it could be in terms of running inspection mechanisms to see what all security aspects are complied with or not complied with. Right? So such kind of security aspects have to be implemented in order to maintain the security posture. And enabling traceability helps in identifying where the potential loopholes could be. Right? And the last one in terms of architecture considerations is cost optimization. So when you're deploying on cloud, there could be sometimes multiple ways of running this application. Like, one example that I mentioned before, you can implement your AMI application on a virtual machine on cloud, or you can move some of your functionality from the application onto serverless architecture. Right? And the cost could be different between running the same functionality on a virtual machine versus serverless architecture, right? And you can decide on the trade-off based on your requirements. So trade-off would mean whether I'm ready to spend more money, but this requirement is important, or you can trade off that requirement to save money. Right? So you can optimize cost by choosing between the alternatives so that you don't spend on something which you could actually do it at a cheaper a price, right? And secondly, you are not spending on undifferentiated heavy lifting, like the data centers, the physical infrastructure, the buildings, the physical security. All this spending is done by cloud solution providers like AWS, and you don't have to spend on those heavy lifting. And secondly, try and adopt consumption model. So consumption model means, you are paying for only what you are using, right? Like for example, a consumption model could be based on number of messages which are flowing through an integration layer, right? If there are no messages, then you're not paying anything. If there are 10 messages, you're paying for say 10 messages, versus setting up a virtual machine which you have to pay even if you're not using it, or if there are no messages flowing through it. So there could be ways of optimizing cost, and that's something that you can do based on evaluating the options available on cloud. So okay, so this is broadly a view of how integration could happen on cloud. So these are various applications which are involved. So on bottom side is the head-end system and different types of data which is flowing in, and the destination systems or the integration systems, that could be OMS, CIS, billing, And the integration between these could be based on different ways. It could be, based on REST APIs. It could be based on, streaming data ingestion, where you want to, ingest streaming data in real time, and you want to analyze the data also in real time. Right? Or it could be, REST API based integration, wherein you would also probably need some message transformation. And integration could also be based on files, right? So the important point that I'm trying to make here is that when you move towards cloud, the flexibility or agility that you would have in terms of implementing your application could be more than what you are doing on premise, right? Say in the case of integration, you probably opted for only flat file based integration, and later you realized you'll have to do some streaming data ingestion. So that's when you wait for another few months before you get that system which can handle, say, streaming data ingestion, right? Unlike cloud, where you have the agility of opting for streaming data ingestion services and get going with analyzing the data in streaming data analytics, right? And similarly, setting up a data lake. So once you're implementing a smart metering application, you should also look at setting up a data lake, which is a foundation for analytics in future. You may not be doing analytics right away, but building a data lake, storing the data, is something which is important, so that you could look at additional use cases in future as you gather more and more data. And this data could be, say, images, it could be CSV files, it could be data from RDBMS tables, which you could use for, say, regulatory reporting, or building, smart meter operation centers, or additional, say, AI/ML based use cases for, say, supply forecasting or TOU segmentation. So many such use cases. Okay, so that is it from my side. This is my email address. Feel free to reach out to me for any further discussion.
Any questions from the audience?
Okay, so how the pay-as-you-use model can be used for deploying HES system? Say, one example could be, you are implementing your HES system based on some of the resources which are available. It may not be just based on virtual machines. You are taking virtual machines, you are installing your HES application and running it, but rather, say, you are deploying some of the functions on AWS Lambda, for example. So it's a serverless compute. So what happens is, say there is an on-demand read function that you implemented on AWS Lambda, right? So you will be paying for the usage of Lambda based on the number of times the function has been invoked. Right? Say, for example, on a particular day, there were no read requests which were initiated from the billing system onto HES, right? So in that case, there are no on-demand read functions which are invoked on HES, so you are not paying for anything, right? So you will be paying only for those invocations which happen if it was invoked, say, 10 times. For an on-demand read request, you are paying for those usage for 10 times. So similarly, there are different other services that you can opt for, for which you are actually paying based on consumption. So once we it could be a more detailed discussion, obviously, but I try to give one example of how we can handle it.